So mm, the assessments are listed here. So the digital assignment will come just before the CAT 1. So that is the final date, and I will give 1 week before. There will be set of numerical problems we will solve, which will be mostly based on the CAT 1 syllabus. So which will give you a good idea about how the questions will be. And then quiz 1 will come in the next week. So that will be largely based on the unit 1, that is electrostatics. So and then quiz 2 will come just before the CAT 2, I think, yes. So all of these are actually you have to write detailed answers. So the quiz and all these things, the timing will be given clearly upon it. So quiz 1 and quiz 2 will be just like Code Tantra, it will be online exam. And so definitely it is, these questions actually will not come anywhere else from the topics, from the slides what I have given. At the same time, it won't be available in books. So the questions always will be new, and but at the same time, it will be means those who are having good experience in the topics, definitely they can crack it. It's very easy, and therefore CAT 1 and CAT 2 will be. And I think you know about that. From September 11th onwards, the CAT 1 will start. I think the October 24th onwards, the quiz CAT 2 will start. So similarly, you'll be having other subjects. Please check it out and plan your all days, including your entertainments, then your other holidays, your travel, everything else you can plan accordingly. Well, so let us go inside the class. We are in electrostatic. We already completed Coulomb's law. Coulomb's law is one of the very fundamental laws in electrostatics. In fact, before Coulomb's law being developed, many of the magnetostatic components, because before electric field, magnetic, and like magnets, everything well before the electric properties itself. That is why magnetostatics actually has come first. Then all the way electrostatics has come, but we always study electrostatics because of its very easy property. Coulomb's law we have studied in a great deal, and using Coulomb's law directly we can find the force and the electric field just around the charged bodies. So these charged bodies actually they will be having different shapes. We have taken most familiar shapes. It doesn't mean that it belongs to a single system. It means these kind of famous structures itself. You can also take any arbitrary structure, but mathematically it will be very difficult. So if you take a arbitrary structure, it will be very difficult. So what people used to do is they will divide into multiple sections. So these are called grids. So you can see that this grid actually will come within the known structure. So for this, we already have the expression for that. For this particular region, we will divide multiple into small. And of course, for that also, we have the idea. So somehow we can make this structure approximately equal to one of these known physical structures. By the way, we can easily get the electric field evolved or exerted out of the this charged bodies. We can easily get that. We derive the expression for that, and we also solved some of the numerical problems with that. I believe you people are started to study, and all the slides are uploaded. Just keep on work on that. It is like more like I always tell that it is like I mean you have to practice like karate, and in the exam you are going to face Bruce Lee. So I hope all of you know about the Bruce Lee's skills. So what he told is he don't fear of people know 1,000 or 10,000 what do you call 10,000 forms, which means different attacking procedures. But he always afraid of the person who practiced 1,000 or 10,000 times of single form, because with that single form he can definitely flat any guys because he practiced that much precise. So like that, you also do practice and always think the Bruce Lee is ahead. of you in the due course. Okay, now we have come to another alternate topic in the same electrostatics itself. So electrostatic is all about how these charged bodies, okay, particularly those which particularly the structure is not moving, static. So these structures, how they react to the other charged bodies or other material systems, how they behave. So this is what always we are going to study, and which is very, very essential for most of the applications. Like for example, when you go and touch some charged bodies, let's say TV, then somebody feels shock. This is because not because the entire cover itself sometimes made up of plastic, and it can be a charged body. So it will simply drain out of your body because your body is a simple or local resistive path to reach the ground. So sometimes we feel shocked like that. So, and these kind of things can be solved easily by this electrostatic problem, and over the years people have successfully developed. That is why we are not feeling any shock or something else. But if you ask your parents, definitely they will say that they are afraid of this electricity all the time, because at those times the systems were not designed with the perspective of electrostatics. So similar to Coulomb's law, alternate theorems were developed, and that is actually evolved well before Faraday itself. But Faraday has described these properties in his own way. Okay, he is completely original in his own way, and he developed the idea of the displacement flux. Okay, what he has mentioned is if you take a charged body, let's say there is a volumetric structure like a sphere, and it is having a radius a, and outside that at a particular distance another enclosing sphere is available, and that has the radius of b. So b is greater than a, and if you charge the inner uh, sphere by positive charges, then within a fraction of a second you will feel that actually the outside will be outside a sphere also will be charged, but it will be negatively charged. And we can surprise that how this could happen. This could happen only by the flux lines or the electric field actually traveling from this charged body to another charged body and completely excited out, and will reach this surface, which is actually a chargeable structure. Like let's say it's a metallic structure. So easily this will be charged, and this positive negative, they always attract each other, and therefore the field will be linked, and outside it cannot go out. Therefore, if you measure the uh, if you measure this conductivity of or the charge structure, it will be negative of the or the opposite of this, the inner sphere itself. So he called this is happening because of the flux. The flux itself, it means that the number of field lines per unit charge per unit area. So if there is a, let's say there is a shape here, and here more accumulation of charges available, and as it goes, the charge density is relaxed. So we can say that the surface charge density here, it is very high, here it is very low. So if you draw that, it is very low, here it is very high, it is. So therefore the electric field will be relaxed here, but here it will be much more denser because of the charges. And if you calculate per unit area, then we will calculate the electric field per unit area. Both are actually vectors, and uh, this we call actually the flux. So this integral or this differential vector with respect to the field lines, how many field lines are available. So that is all named as flux, and it is actually flying from one place to another place. So in Faraday's notebook, in many places he has mentioned as flu, which he alternatively mentioned as the instead of electric field, he has mentioned as field flux or flu, like that. And so that is what people named this property, that uh, the flux or the unit number of field lines per unit area that is named after the flux. And since this concept is true, therefore the flux, which is actually total flux available within or exerted out of this charged body, which is the total. Okay, so the total, and directly it will be equal to the source charge itself. So that is the first theorem being introduced by uh, Faraday himself, and this is actually true in multiple ways, at least in ideal condition. But before that, before him, many people already developed this theory in fact much more in better way. And Faraday has come up with some experimental aspects out of that. In fact, in the very similar manner, many systems works, including battery and other things. So this electric flux, if we can define properly for a given system, then better than Coulomb's or easier than Coulomb's law method, we can easily get the electric field. Or if we know the electric field, we can calculate the charge or charge density. All these things actually we can easily find out of the given system. And in case of this, all integrations or differentiations, if you feel this all tricky or a little bit difficult for you, then alternatively we can choose uh, uh, this flux method. So this is the alternate method. We can always say it is the alternate method for Coulomb's law. So how to define this electric flux density? So the electric flux density, for this we supposed to know the charge of the source system or the charged body. Okay, and if it is uniformly distributed or non-uniform, that doesn't matter. So it is having a surface area, and this surface area which is going to define the flux which is coming out of that. So if you take any particular charged body with the total charge of Q, and always this flux is going to be perpendicular to the surface, whatever you are taking. So if this is the surface you are taking ds, and this ds will be having a vector, and which is the normal vector. So this along this normal vector direction only, we are going to get the flux density, which is often mentioned as D. So electric field E and flux density. So you can always call this in density or field density, that is often referred as the D. Okay, so this D vector is always going to be perpendicular to that, and this makes this theorem much more or these concepts much more easy to integrate or differentiate while comparing the Coulomb's law. So, but Coulomb's law can be used for some different applications, and this electric flux density method can be used in the other way. So, for example, for this particular charge body, so we can easily say that we already know the total flux which is induced and divided by this 4 pi a square, which will give the D. So this is the magnitude of that. And since this is correct, then you can replace this psi with Q, and that is what. Okay, so you can easily see that Coulomb's law behavior already comes into the picture. And so this is the differential form, and you can also do the integration over this surface. Okay, so it is always a closed surface integration. So always we have to use this circle here. So if you take a closed surface integration of the flux which are coming out of this charged body, and then you will get the total flux. This total flux will be equal to Q. So what is the meaning out of that? Assume that I have a randomly shaped body which is charged. Okay, and this charged one is always going to exert the field in all direction, and this will be perpendicular to the surface, the local surface. Here the local surface is different, here the local surface is different. However, this flux will be always perpendicular to that. Now my objective is to calculate the total flux available or exerted out of this charged body. How to do that? It is very simple, that we are going to draw a surface just around that. Okay, the surface supposed to be drawn and in such a way that It will capture all the field components. It should not ignore any field components. Let's say we are actually taking some rectangle. Let's say if you are taking the rectangle one, then the one which is going to through this corner, it is very difficult to define that. Okay, because while integration we may miss this, but if you draw a sphere, definitely we can get all the things, because this perpendicular components, again it is perpendicular to the or it is parallel to the surface of the sphere itself. So we can capture all these things. So by properly choosing a enclosing surface, and if you integrate over the enclosing surface, and we are going to choose the enclosing surface as a very known structure like sphere or cylinder or a cubic one or some rectangular structures in whatever the preferred way we can. So by doing so, we can calculate all the flux density, and if we integrate over that surface, known surface, it will be very easy to get the total flux, and that total flux is going to be the charge. So this can be very useful. If you know the flux density, you can calculate this Q, or if you know that, you can calculate this flux density. Either way, it is very same as that of how we do for the Coulomb's law, which utilizes to calculate the electric field. So in many cases, people argue that this method is the reverse method of the Coulomb's law. So the Coulomb's law will tell that if you know the Q, then you can calculate the electric field. Here, if you know the electric field, which is nothing but d by epsilon naught, and you can calculate the Q, or both can be done in opposite way, but this is very easy way, and this is very easy way, and in the opposite side it is tough, it is opposite. So whichever the application you are going to do, for example, whenever you construct some structure such a way that it is going to avoid the electromagnetic interference for a mobile phone or a mic or a laptop or whatever it is, then if you know the electric field which is coming out of the system, which is interfering system, then you can easily see the charged body, and you can use this flux density method. Or if you know the charging or the current distribution inside that, then you can easily calculate the electric field out of that. For that, you can use the Coulomb's law method. So whichever the method you feel convenient, or you feel depends on the application that you see, then you can utilize that concept. So this is the simple way we can utilize this electric flux density method. And that is what we are going to study as a Gauss law. Gauss law actually well before Faraday itself, even about at least 200 years before Faraday itself, Gauss actually clearly has mentioned about the flux in the other way. Okay, so he has mentioned as the uh, the uh, the flux or the intensity of the uh, field which is coming out of that, and this is actually given completely by vectorial method itself, and this actually originally started by Lagrange just after defining this the properties of the fields all the way, like gravity and all these things. He has demonstrated many differential equations. In fact, the most of the collected works of the Newton was means readdressed or reprinted by Lagrange. And in fact, you have studied many Lagrange theorems of Lagrange, and he has coined one of the integral method of a particular closed surface. So if you want to integrate a closed surface, then you can take the volumetric integration. Or if you want to study the volumetric integration, you can consider the closed surface integration. So like that actually has introduced. And this is later, after 100 years later, Gauss has come up with a very simple mathematical, powerful mathematical procedure in terms of differential calculus and integral calculus. So what this Gauss law states is nothing but the total flux psi through a closed surface. Okay, okay, and it is equal to the total charge enclosed by that surface. Okay, so here it means there is a charged body and there are many charges available, and this is actually enclosed by something. So this is having a particular area. Let's say we will call this area as A. Okay, and this is completely arbitrary shape. So it is very difficult to define the shape. But what we are actually going to do is we are going to draw a new surface. Okay, so this new surface we are going to call Gaussian surface. Since we are going to use Gauss law, and this surface is often referred as Gaussian surface. So this Gaussian surface we are going to draw, and this is a always people in the book they will draw always arbitrary, but you can choose in your own way. For example, you can draw some sphere or something else you can do. So this is we are going to call that as a surface. Okay, and this is Gaussian surface, closed surface. You can call by any name. And in books, you can always refer. For example, in height, you can see that Gaussian surface. Even in Sadhikyu also, you can find this Gaussian surface name. Okay, so we are going to draw a Gaussian surface, which is a closed surface, and it is drawn in such a way that it encloses the charged body or the the distributed charges uniformly, non-uniformly, whatever it may be. And it is going to have a total charge of Q. And the field which is exerted out of that, okay, we are going to calculate this d psi, which is nothing but capital. Okay, now we are going to integrate this over this closed surface, and we will get the total psi, and that is going to be the Q. So that is what it is described here. So the total flux density, which is closed surface integration of or the total all the flux which is exerted out of the charged body, which can be calculated by this. So in that is equal to the total charge enclosed, and this total charge enclosed we are going to integrate by this volumetric integration. So therefore the total flux is equal to total flux enclosed by the closed surface. So that is what the Gauss law itself. Okay, so this Gauss law, again, it clearly can see the linkage between this closed surface integration and volumetric integration. And this problem can be easily solved by applying the divergence theorem. In the very beginning, we have seen various theorems out of the differential and vector calculus, and one of that is nothing but divergence theorem, often referred as Gauss divergence theorem. So this divergence theorem says very simple thing that if you want to calculate a closed surface integration of any particular vector, and if the closed surface is clearly defined, then you can alternatively you can do the volumetric integration by taking the divergence of the particular vector. So this is the vector of interest. First, I am calculating the divergence of that, and I am going to integrate over the volume. In order to give understanding, let's say I have a cube and it is having a charge, okay, Q, and it is going to exert field in all direction, and that is nothing but the electric field, and which is nothing but d by epsilon naught. So here we define d. Now I supposed to collect all the fields. So here I can't use any sphere, but I am going to use a very big cube, and the very big cube, and I have, if I calculate the big cube which is drawn outside, which we call Gaussian surface, and this integration, okay, so this total surface you can calculate uh, easily, and you know this d vector, therefore you just take the divergence of this d vector. We know this, what is del operator, it is nothing but dou x by dou t ax vector plus dou by dou t dou by dou y ay vector plus dou by dou z vector. So if you integrate, then you can easily separate all the field components, and by integrating over that, so this dot product will give a scalar one, and therefore if you integrate, you will get the total, and which again is going to be this total charge itself. So that is what, and we can see that this is Gauss law and this is divergence theorem. When you compare this, then you can easily see that this integration and this integration. So you can see this is uh, volume integration, this also volume integration. By this way, you can cancel out both the integration, and you can take only the interest of the integration. That is nothing but here it is rho v, here it is del dot d. So by the way, you can easily get this rho v, the charge density, the surface charge density, or the volume charge density of the given charged body is nothing but del dot D vector. So this D vector, if I know, then I can calculate this. Otherwise, if I know that by this by other way, we can by calculating the total flux density, I can calculate this T. So alternatively, we can do this. But most highly preferred one is we know D. By the way, we can calculate this rho, and therefore we can calculate this Q. So that is the idea behind this Gauss law. So Gauss law is a very useful idea while comparing in practical applications. Gauss law often used, and after Gauss, many theorems in the differential form, particularly in the two-dimensional form, many operators been evolved, and that is used in the way most of the practical applications like capacitor, inductor, all these things we can utilize those. So there comes the Green's theorem. So we will study Green's theorem maybe in the end of that. So where you will tend to recall this Gauss law again. So how to use this Gauss law in some applications? So what you have to do is you have to first identify the source charge. Okay, the charge which is going to give the electric field or going to excite the electric field or the flux lines. So we have to identify the source charge and its shape. Okay, and the shape is going to tell us what type of coordinate system we have to choose. Let's say here it is an infinite charge sheet, and this infinite charge sheet, and you can it is very preferred to define with respect to Cartesian coordinate system. And you have a charged ball of a sphere like that. Then you can, it is best to choose the surface also in the sphere. Therefore, cylindrical coordinate system is, sorry, spherical coordinate system is much more preferred. And if you take a line and we have to calculate the electric flux which is going out of that, then we can choose the Gaussian surface as the sphere one, so sorry, cylindrical one. Therefore, cylindrical coordinate system is high. So it is up to one's smartness how to choose this coordinate system, and therefore the Gaussian surface. By doing so, you can very quickly, if you take Coulomb's law, if it takes, let's say, 1 hour, then with this Gauss law, you can easily finish in 15 minutes itself. That much easy it is, but it is a little bit tricky, and therefore sometimes we need to do some approximations as well. So we will see through some examples. So the very first step is to define the shape as much as possible in mathematical form, and therefore we're supposed to choose the coordinate system. Then we have to draw a closed surface. So this closed surface, what it is shown here, it is very difficult to represent in mathematical form, but these closed surfaces it is very, so we're supposed to make a closed surface which is easy to represent mathematically as well as easy to integrate. And if we do integration, if we can utilize some identities, we can easily solve the problem. So like that, we have to choose the closed surface. And this closed surface often referred as Gaussian surface. So this Gaussian surface, if you draw cleverly, then it is very easy. So based on the interest, interest means in terms of the shape and the coordinate system, we are going to draw the shape. And in some places, we can even draw multiple Gaussian surfaces. For instance, there are two concentric spheres. Okay, this is one sphere, another sphere is there. Now we have to, this is actually, let's say, positively charged, and this is negatively charged. Then what about the total flux lines out of that? So we can draw multiple, one Gaussian surface inside, another Gaussian surface outside. So this is 2 or 3 multiple Gaussian surfaces also we can draw. That is up to us. Here you can see that there are multiple Gaussian surfaces are available. So here, this is one surface, this another surface, this another surface, like that. Altogether, we have made a closed surface. So it is up to us, and we have to keep in mind that this D vector is always perpendicular to the surface. So this is infinite charge. So with respect to a small surface which we consider, the flux or the flux lines always going to be perpendicular. So here, if we have some random shape, then here it will be like this, here it will be like that, here it will be like that. So it is always going to be perpendicular. So keeping these two things in mind, we have to draw the Gaussian surface. Once we define the Gaussian surface, then we have to calculate the small surface area vector we have to find. So we can see that there are about 6 surfaces available in this cubic structure. One is this upward one is downward one, and this sidewise. So they will be having different ds. So this ds is vertically oriented. So this ds is nothing but y z. So dy dz, and its normal vector is going to be ax vector. So that is the ds vector. So we have to find this ds vector of the Gaussian surface. Once this is done, then the d should be known to this. Most probably this d will be given to you. Then if you multiply this, then you will get the you're supposed to take the dot product because both are vectors and it's supposed to result here scalar. So we are going for this dot product. So this two vectors, when we take the dot product, then you will get x scalar one, and that we are going to integrate over the closed surface, this Gaussian surface. That is very easy. So these are the things we have to do while using the Gauss law. And if we take some simple examples, we will understand. Then we can go a little bit tricky applications or numerical problems. We can see that. So it is first we'll start with the point charge. So a point charge, we know that it is always going to exert the field in all the directions. And we are going to take a point charge, and it is going to have a total charge of Q. And it is going to exert the flux density in the outward direction. So 360-degree direction, it is going to do that. So first we are actually defining the shape, and for this we have to choose the coordinate system properly. So even though it is drawn with XYZ axis, you can see that the Gaussian surface is selected as this is the Gaussian surface. So this Gaussian surface is selected as the cylindrical one. So if you prefer cylindrical coordinate system, which is very easy. So the point charge is taken, and we are actually first defining this d vector. So this d vector is nothing but this d, which is the radical one with respect to this ER vector. Okay, and if you take in terms of XYZ axis, this ER vector is very difficult to do. So it is very easy in case of the spherical coordinate system. So that is what it is done first. Then by using this Gauss divergence theorem, we can easily say that this total charge Q is nothing but the integration of all the d vector with respect to the surface, the Gaussian surface, the small surface which is considered from the Gaussian surface. So when we are taking the dot product, and when you take the dot product, this d is always going to be constant in all directions. So this d is taken outside, and this d vector, which is ER vector, and the small surface which we are going to consider, we know that it is going to have this ds vector is going to be r square cos theta d theta d phi. So this is the small surface, which so I believe all of you know about that. So if you take any particular place, so this is one and this is one. So the vertical one, which will be nothing but r cos theta d theta, and this horizontal one will give r d phi. So when you multiply, you will get r square cos d theta d phi. So this is this anyway will be having AR vector as the perpendicular vector. So we are going to multiply this ds vector and this d vector. When you do that, you will get d, the magnitude, and this AR vector going to be multiplied will give 1, and this integration. So solely your integration of this ds matters. So when you do the closed integration, it is other words, you have to calculate the perimeter of this sphere, which we know that it is nothing but 4 pi r square. So when we do the integration, you will easily get that. And therefore, okay. ds will give sine theta r square. Okay. So this will give cos theta or sin theta. So this is theta. Then this is r square. So if you draw something perpendicular, then this and this r by 2, r by 2. Yeah, so this is this is sine theta. That is why it is given here. So we will get 4 pi r square. So which is going to be our q. And therefore, if you place this in the denominator, you will get this d. Okay. So and you can also add this AR vector, and you will get that. So I believe you can easily recognize the Coulomb's law here. And this look like a detailed derivation for even for a simple point. So for this, if you, for example, for this point charge using Coulomb's law, we already have the expression. So we need not to use this Gauss law here. So we have to think because we know both the methods, Gauss law as well as Coulomb's law. And if we know for a given structure, very well we can take this Coulomb's law method. But if we do not know, then we can go for Gauss law method. Let us take some other example. So here is the example with infinite line. So we have seen that for a finite line, how we have done the detailed derivation of that. So this particular derivation, I believe you know that. Then if you make it infinite, what will happen? Because if we directly take infinite, it will be very difficult to pursue the results directly. So we do not know how this particular vector will be cancelled, that we cannot directly define that. So always we supposed to define this z direction. Then we have to cancel if we draw for infinite line. But here in case of the Gauss law, so what we are going to do, we are going to take a infinite line charge. Okay, so this infinite line charge is having a uniform charge density of rho L. Okay, so and along the z axis. Okay, so now we have to calculate the flux density or the electric field which is exerted out of this infinite line. So we already know the expression for that. We should see that how short we are actually getting that. So for this particular one, we are actually going to choose the cylindrical coordinate system because it is very easy to go around that with respect to the point P of interest. So if the point P is here, you can easily draw a cylinder out of that. And you can draw the field which is exerted out, and you can easily get the integration done. By doing so, you will get the D easily. So we are actually going to take this D vector. First, we have to define the D vector. It is not necessary to calculate the D vector, but the way we are defining that. So according to the Gauss law's principle, the D vector, that is the flux lines, always will be perpendicular to the structure what we consider. So even if it is a small or big one, so we are always going to consider this perpendicular lines alone. And in this direction, definitely there is no field component available according to the Gauss law. So this is what we are going to see. So this D vector is always some magnitude. Okay, so let us take this is D naught something, and with a rho vector. So this is the vectorial representation of the flux density. So this is actually we have the justification that this field is going to be constant throughout that, and as well as because since it is a uniformly charged, at the same time this D will be always normal to the surface. Therefore, this can be represented. Then we have to once we define this, then we are drawing a Gaussian surface. So we have this is the Gaussian surface. And this Gaussian surface is, we can take any arbitrary size. It need not to be exactly this. So we have taken arbitrary radius of rho, and we are going to consider a length L. This length L can be defined infinite in future, or we can take it as a finite structure itself. That's not a big deal. So we are actually taking a finite length, and it is going to be just around the structure. Now the next step is we have to define the surface, a small surface which is considered on the or which is taken out of the Gaussian sphere. So there are actually you can find there are three surfaces available. One is this surface, another one is this one which is just around that, and in the bottom also you have the one surface. And we know that this d component is going to be perpendicular. Anyway, the d component which is going to be available on this is going to be 0 only. So that is what we are actually defining here, that this the top surface and the bottom surface are going to have this total amount of 0 flux density out of that, since this d vector is perpendicular all the time. So only we are going to see in the side direction. So in this direction, what flux is coming out of that. So now we have to define this. So ds vector. So it is simply nothing but rho d phi dz a rho vector. I believe you can easily see that. So this is the horizontal one. The vertical one is d dz vector. By multiplying that, you will get the surface vector. And this surface vector and this d vector we are going to multiply. So this is already we know that it is nothing but d naught or something d. Here it is mentioned as d rho. So we will use the d rho itself, d rho a rho vector. So we are going to take the dot product. When you take the dot product, you will see that this two unit vector, they multiply each other, become one. Then we can say that the dot product of the d vector dot ds vector is going to be d rho into, or we can say this rho d rho d phi dz vector. Okay, now we have to integrate that. So we are going to integrate over this phi. So that is what actually we're supposed to do. And with respect to length L. So this is what we are actually, this is the side one. So the z vary from 0 to L and the phi vary from 0 to 2 pi. So when you integrate that, you will easily get that. Since this rho and d phi, they are d phi and dz are independent each other, we can easily differentiate separately. So this 0 to 2 pi is going to give 2 pi, and this 0 to L with respect to this dz vector, it is going to give the L, and this rho, it's already there, and dr vector. So here we can mention as a d rho vector itself for continuity. So d rho vector is d rho is available. So this is the total, and that is going to be the total charge enclosed. And this total charge enclosed over the surface, we can easily see that it is nothing but the rho L, and which is uniform in all the directions and with respect to length L. So we are actually having, so here this length L and this length L, when you cancel, you will easily see that this d rho alone you can take it out. So this d rho is nothing but rho L divided by 4 pi this. And this, we already know that this d is nothing but epsilon naught E vector. Therefore, we can easily calculate the electric field. And I believe you can remember this expression. This electric field is nothing but, sorry, this is the magnitude of the electric field. So we can draw the electric field is nothing but rho L divided by 2 pi epsilon naught rho. So this is actually very easy method for this particular application for line vector, that to infinite line vector, by simply let's say this is the first step we are doing, second step, and in the third step we are getting that. In between, actually we are going to do one more step here, and we are specifying this. If you take 5 steps altogether, we can easily see that the expression has come very quickly. But the same expression when we do for a finite structure. So for a finite line, if we are covering with this one, then here once again we supposed to consider this vector also, because the field will be exerted out of this small area, and the small area, if it is equal to 0, then there will be a question about this will come, and it is purely depends on the location of the P point itself. So so that is what I am always saying, that this Gauss law as well as Coulomb's law should be considered with respect to the application perspective. Here is another example that there are two cylindrical, the coaxial cylinders are there. So we are having an axis, and in that one cylinder is there, and just above that we have one more cylinder. Now we have to calculate the flux line which is going from this to this, where this is positively charged, this is negatively charged. In that case, what will happen? Or we know only this is inside that it is positively charged because I have connected a battery here and another battery is just, let's say it is connected here. So how the flux lines will form just around that. So if I draw the Gaussian surface just around that, then I can easily calculate the total charge Q. And so I'm leaving this derivations to you. It is available in this W Heights in the book. It's very nicely it is given, so you can study upon that, which will be very similar to that of this. There is no big difference, very similar, but here the radius of this first cylinder and the second cylinder is coming to the picture. So you just go through the text and you will easily understand that. Now we are coming to next application, that if we take a sheet, infinite sheet, then how we can calculate the electric field or the flux available from that. So we are going to take a infinite sheet which is having rho s surface uniform charge density of rho s. And for study purpose, actually, we are going to take a very small surface. Okay, so this is the small surface we are going to consider. And we know that the flux always will be perpendicular to this in the vertical direction or a horizontal direction. Only in the horizontal direction or in any other direction, the flux component will not be available. So in dy vector as well as dx vector, sorry, y direction as well as x direction, there is no component available. The component will be exist only in the z direction. So out of this d vector, we can easily say that it is going to be ds. Since it is a surface one, we will call that as a ds and this az vector. So this is how we are going to define that. And it is very much we can see that it is very easy to define with rectangle coordinate system. So we can go with rectangle coordinate system itself. Otherwise, we can also use cylindrical coordinate system by drawing the cylinder here. We can also draw with respect to that. So anyhow, here also it is going to be perpendicular over the small surface which we consider as a closed surface. So we are actually defining the d vector. Then we have to define this ds vector. So what is this ds vector? You can see that there are about 6 directions. One is this, and the other direction. So one is along the plus y, another one is minus y, another one is plus x, another one is minus x. In 4 directions, we have the field area, and along the plus z direction, minus z direction. There are about 6 faces for this cubic structure, and therefore that many areas are available. But we know about that this vector is d vector is defined only in the perpendicular directions along the z direction. So in the other directions, the dot product will result to 0 only. So there are 2 ds vectors available. One is in the positive side, so we will call that as a ds positive, which is nothing but dx dy and this az vector, and another surface is available, that is we can call it as in the negative direction, that is ds, which is nothing but same dx dy, but minus we have to put this az vector. So that is what it is mentioned as top and bottom, both supposed to be done in the opposite way. So when we integrate total, we will get 2 times of the area. Welcome. Okay. You just ignore the this vector because this d vector will be definitely opposite side. So you will see that this d vector into ds vector positive will give ds into area, and this is this direction, and in this direction we will get negative d vector. So this negative d vector and this negative ds vector, just -1. This also going to give the ds vector a1. ds a only is going to give, that is the total. That is the total flux within the given area of A. And if you add this 2, you will get 2 times of that. And within this closed surface, you can calculate the total charge available. That is going to be the Q. And by the way, if you cancel out this A, then you will easily see this as ds is equal to rho s by 2. So that is what, and you can put the vector. This d vector is going to be rho by 2 az vector. And in terms of electric field, it is nothing but rho s divided by 2 epsilon naught. So here the advantage of this Gauss law method is we are actually going to choose a suitable Gaussian surface such that the desired results will come very quickly. In case of Coulomb's law, we supposed to consider all the directions because there is no definition for the surface or any desired direction or like that. It is not specified. But the moment we see that the desired direction or the desired results are a little bit understood, okay, then we can easily draw the Gaussian surface. And the Gaussian surface is going to help us integrate very quickly. And we can easily get the total surface. So the same problem if we consider for a rectangular box, okay, a rectangular box is available and the total charge is q. So you can easily draw another big rectangular box, and with respect to, there are about 6 surface will be available. For this surface, one integration, this surface, one integration, totally 6 integrations when you perform, then you can get the total closed surface integration, and you can easily get that. But the same problem when you do with Coulomb's law, it will be very, very difficult. So that is the interesting part of the Gauss law. So, but anyhow, it is subject to the application. And this is a very interesting problem in case of Gauss law, that if we take a uniformly charged sphere, then how we can calculate the electric flux available inside the sphere and outside the sphere. Here again, I have done a mistake. This is sign. So what we are actually going to do is we are going to consider a sphere, and that sphere is charged uniformly throughout the sphere itself, which is with the charge density of rho v. Okay, so we are going to take a solid ball, and the solid ball is completely filled with charges of uniform distribution of rho v. Now we have to calculate the electric field inside the sphere as well as outside the sphere. So we are considering the sphere with radius of a, and in order to calculate at inside and outside, we are going to take a arbitrary radius, and we are going to draw a sphere. So this sphere, we are drawing one inside that. This is the Gaussian sphere or Gaussian surface, and here this is the Gaussian surface. So you can see that one is drawn inside, one is drawn outside. What's the difference is when you draw inside, the radius is smaller than a, and when you draw outside, the radius is more than or greater than a. So both are actually completely different problem. Now we supposed to calculate the electric field exerted out of that. So for this, we are going to simply first do the integration over the closed surface, the Gaussian surface which we consider. So even though the total radius is a, we are actually going to consider only for the r itself. So that is what we are actually going to do this integration 0 to 2 pi, 0 to pi, r to 0 to r with r square sine theta d theta d phi. That is what we are going to integrate. When you do the integration, you will get this integration result, which is nothing but r cube by 3 and sine theta. These are going to give this 4 pi. So rho naught is nothing but rho v, which we consider as a charge density. And we are going to apply the Gauss law. So according to Gauss law, this is the integration is nothing but total d. So if we know the closed surface integration, we can calculate the field exerted out of that. Okay, so this, we know the surface of this, and we are going to integrate just over the surface. We will get 4 pi r square. That is the periphery of the or the perimeter of the sphere, and therefore this let's say this is the equation number 1 and this is the equation number 2. Both are same. When you compare this, you can easily find out this dr. So this dr is going to be, so you cancel the 4 pi r square, this will cancel. So you will get r by 3 rho naught, and add the vector, the only the exactly this sorry, r vector. So this r vector component alone is going to be available, and this expression solely applicable 0 to a only. Okay, within that only it is applicable. Outside that it is not applicable. Why? Because this integration does not valid for outside. Why? Because this charge density will be available only up to a. Outside it won't be available. So when we do for this uh, r greater than a, so when you do for this particular case, the charge density will be available up to here. After this, it is going to be 0. So whenever you integrate over this surface at any time, at any radius, we can account only up to a. So that is why we will always get the total charge is equal to rho naught 4 pi a cube by 3. Here it is r cube by 3. So you're supposed to know this difference. Then we are actually applying this very same integration for outside. So we will get this d 4 pi r, and here it is a cube. So this dr, we can bring it to the downside. We will get this expression. Here the problem is it is linearly increasing with respect to r, and it is linearly decreasing with respect to r square. The same d vector is inside, it is available in different way. Outside it is available in different way. So if you take a sphere of radius a, then when you start from the center, if you go up to the radius a, this electric field or the flux density will keep on increase, and it will reach the maximum value of a by 3 rho v. But just after that, this charge density stops. So therefore, the electric flux tend to decay in terms of r square. So this is the interesting problem. So you can go through the book and derive few more problems are available in terms of Gauss law. So we will see some numerical workout with Gauss law in the next class. I believe I have taken too much time. Sorry for that. And in the next class, I will answer for all your queries. Thank you.